Welcome to this webnote on topological dual of vector spaces. This concept of dual of a vector space is crucial and central to the study of normed vector spaces or Banach spaces in function analysis. And moreover, not only that, we have one more issue, which is sometimes the norm topology or the strong topology does not behave very well in infinite dimensional spaces. And these topological duals, they offer weaker topologies that behave very nicely. So the properties of these dual vector spaces is crucial to anybody who wants to learn about the basics of function analysis spaces. So let me set the ground here with the basic definition. Throughout, X will be a normed vector space. So let X be a normed vector space. Of course, this concept of topological dual can be defined for any linear vector space, but we focus here only on normed vector spaces. Okay? Consider the Banach space Bxr. So this is the space of all continuous linear operators. Here we're taking R, the set of or the field of all the scalars on X, but definitely we can extend this again to the case of complex scalars, or what we call complex vector spaces. But throughout here we will just focus on the real case and the real vector spaces. We have a notation. This Banach space will be denoted X bar or X prime. Okay? And it is a Banach space, and we have the norm operator. The elements of X star will be denoted by F, G, etc., or X star, Y star, etc. Okay, we will not call them any X star in X star will not be called continuous operator, linear operator. We'll not use the word operator here, okay? But we will say X star is a continuous linear functional. Let X star belongs to X star. Then the vector space R of X star, the range, okay, is a subspace of R, a one-dimensional space. So we have two cases. Either the range is 0, which means that X star is 0, or the range is R, which means that X star is surjective. Okay, so if X star belongs to the dual and x star is not equal to 0, okay, which means that the norm of x star is greater than 0, the operator norm, then in this case we have x star of x equals the range of x star equals r. Okay? If we consider n of x star the null space equals the kernel of x star equals to x in x, such that x star of x equals to 0, then the quotient space is isomorphic to the range. So it's a one-dimensional space basically, and in fact we have moreover. Okay, let x0 in x such that x star of x0 not equal to 0, then we have something very interesting. We have x, which is equal to the null space plus direct sum r times x0. So we can prove it, which means that this is what we call codimension 1 subspaces. So n of x star has codimension 1. So in other words, if you add one dimension to n of x star, you get the entire space, and this is known as a hyperplane. So recall that codimension 1 subspaces of x are called hyperplanes. Okay, so we have of course two concepts of hyperplanes. We have the hyperplanes which contains 0 and hyperplanes which do not contain 0. They are not subspaces, of course, if they don't contain 0. Okay, but they are what we call affine hyperplanes. Huh? Okay, one more notation that I may use or may not use. Okay, for any x star in x star, okay, x star of x, we will use this notation x star x or x star. Okay, it's just notation, and of course this notation here was inspired from the Hilbert spaces, so we borrowed it from the Hilbert spaces. Next, we have a beautiful problem. Given X a normed vector space, is there something in the dual, in X star, which is not equal to 0? So is there an element in the x star such that x star is not equal to 0? Okay, I just mentioned the word, so let's just do a definition. I should have done it before, but so definition, x star is called the dual of x. Okay, so if x is a normed vector space, we know that x star is always a Banach space, from what we learned before. So here now the question becomes, is there a non-zero linear functionals, continuous linear functions defined on X? And this was answered by Anne and Banach. Okay. So let us discuss this theorem, which is at the core. It's one of these fundamental theorems. I did not add it to the fundamental theorems of in-normed vector spaces like the open mapping theorem or closed graph theorem, etc., or uniform boundedness principle, because this is related to the dual space. So I kept it for the lecture on dual spaces. Okay. So here we are going to give a more general version of this theorem, which will answer, of course, the problem that we just stated. Okay. So here let us give the general theorem. Let X be a vector space let P be a function from X into R such that number one, it is subadditive. Two, P of alpha X is equal to alpha P of X with alpha positive. For any X, Y, and alpha, we have these two properties. So be careful, P is not semi-norm because we don't have P. In fact, assuming number two, we get P of 0 equals 0. Okay, but we're not assuming that P of X is positive. Next, let M be a subspace of X. Let F go from M into R be linear such that F of X is less than P of X for all X in M. Then there exists F hat from X into R such that F hat of X less than P of X for all X in X, and F hat of X is equal to F of X for any X in M. So it's an extension. It's an extension of F, which preserves that inequality. This is the most important part, is this part here. Proof. Let assume X different from M. Okay. Otherwise, there is nothing to prove. If M is equal to X, then there is nothing to prove. You take F hat to be F. Okay. Let X0 belong to X minus M. So we take a vector which is in X, not in M. And we take Y to be M, and we add to it r x0. So we add one dimension to the space M, and we're going to try to extend F to the subspace Y. So this is the goal we're going to do now, okay? So clearly for any x in Y, there exists M in M and alpha in R, such that x equal M plus alpha x0 a unique fashion. In a unique fashion. So we have f hat, if it exists, is going to be f hat of M plus alpha f hat of x0. And since it is an extension of f, we're going to have this as f of M plus alpha f hat of x0. Okay? So we only need to find, okay, we need to find f hat of x0 equals to a, which belongs to R. So this is basically a real number. Not only that, we also need to satisfy f of M plus alpha a less or equal than P of M plus alpha of x0 to preserve the inequality. Okay? So if alpha is positive, so here, if alpha is positive, okay, we get a less than P of M plus alpha x0 minus f of M over alpha, which is equal or a less or equal than P of M over alpha plus x0 minus f of M over alpha. Okay? Which means that for any M in M, we must have a less than P of M plus x0 minus f of M. And of course here I use the linearity of the subspace M to see that M belongs to M if and only if alpha M over alpha belongs to M. If alpha is negative, if alpha is equal to minus beta with beta positive, in this case, similar calculations, we get, in this case, we get A is greater. So here, f of M plus, minus, sorry, f of M minus P of M minus x0 is less or equal to A. Great. So, okay, which means that for any we must finally, if we put everything together, we get for any M1, M2 in M, we get that f of M1 minus P of M1 minus x0 less than A less than fp of m2 plus x0 minus f of m2. So this is the condition for which if such a exists and satisfies this, then we get exactly the extension we are looking for. Okay? So to have this, we need to show that this sup is less than the inf of this one. So sup of f of m minus p m minus x0, m in m, is less than the infimum of p of m plus x0 minus f of m for m in m. If this is satisfied, such a do exist. Okay? So let m1, m2 belong to m. Then f of m1 plus m2 is less or equal than p of m1 plus m2. So here we're using our assumption on f defined on m that you have this control by p. Okay? Linearity of f gives us what? Then f of m1 plus f of m2. This is less or, and now we are going to use this is equal to m1 plus x0 plus m2 minus x0. Okay? And then we use the inequality, the subadditivity of p. So this is less than p of m1 plus x0 plus p of m2 minus x0. Okay? So f of m2 minus p of m2 minus x0 is less than p of m1 plus x0 minus f of m1. So we have from this, for any m1 and m2, we conclude from the properties of the real line that we have the sup of this set less than the inf of that set. Okay? Because this is just properties of lattice properties of the real line. So such a exists, therefore f hat from m plus r x0 into r linear do exist, which extends f and preserve that control by p. So now let us go and prove in fact that we have an extension to the entire space. So if we have a linear map on a subspace, we can add one dimension. This is the proof basically. And from there is just a zone application of the zone classical lemma. Okay, so let's consider the family F. So here, extension to X. So let F be the family of the pairs Y and H such that H goes, such that Y is a subspace, Y subspace of X with M subspace of Y. H is a linear function from Y into R, linear, such that H restricted to M is equal to F, so it's an extension of our map F. And we have the control and H of Y less than P of Y for any Y in capital Y. So we consider this family. This family is not empty because M F belongs to F. Okay, and now we order. Okay, so we order. So we take Y1 H1. Let yi hi in F, I is equal to 1, 2. We write this is less than y2 h2 if and only if y1 is a subspace of y2 and h2 restricted to y1 is equal to h1. So h2 is an extension of h1. Okay? It's very easy to see that if y alpha, h alpha, okay, is a chain in F, okay, so it's a totally ordered family, so gamma is totally ordered, then in this case we can take y, which is the union of all the y alpha, and that is because it's a totally ordered set, so you get here a linear subspace which contains M because all of them they do contain M. And okay, if we take H from Y into R such that H of Y equal H alpha of Y whenever Y belongs to Y alpha. So if y belongs to capital Y, it belongs at least to one of the y alphas. And then we take the h alpha of y. So someone will argue, what about if it belongs to two y alphas? So which one do you take, h alpha or h beta? And since the set of index gamma is totally ordered, so the y alpha will be a subspace of y beta, for example, and now we use the property that h beta is an extension of h alpha, and therefore we have the same. So this choice here is independent of the index alpha. Okay, it's independent. There is no problem, and we can see that y h belong to f. So it is h is linear, it extends M, and you have that control, of course, all this because of the h alphas, and y alpha h alpha, all of them are indeed smaller than y h for any alpha in gamma. So any chain has an upper bound, so zone lemma implies the existence of a maximal element, in F. Say y h is a maximal element. Okay, so the claim here, we claim that y in fact is equal to x. Assume not. Okay, then x is different from y, and the previous proof shows that there exists x0 in x minus y, and let's call it h hat an extension to h such that the yh is less than y plus rx0 h hat, with this here belongs to f. So you see here what we found. from the beginning, the earlier part of the proof, that we are able to extend this function h, or this linear function h on y, to the one-dimensional space y plus r of x0. And clearly, since y is different from y plus r of x0, this is an obvious contradiction with the maximality, of yh. So clearly then, so y is equal to x, and h is just the f hat we're looking for. So we found this extension to the entire space, extensions to f, with the control. Is very important with preserving the control. Usually the extensions do not preserve. They have bigger, they don't have that control, okay? It's a very fundamental theorem. Remark. Here, I want to just make a quick remark here. What is the key in the proof? Okay, the key in the proof, the second part, where we use the lemma, is a kind of set theoretical approach. It's very common and used in different areas in set theory, for example. But the key here is the first one. The first one is this proof here. Okay, the proof about how to extend it to one dimension. And to be honest with you, the proof has to do with what's boxed there. So it's a property of the real line. Okay, and when you look at carefully this property, it means that we have these intervals. Okay, so the intervals, just for the sake of, if you take this interval here, this one with this one, okay, so you get intervals, and all of them shall contain a, and which means that the total intersection of these intervals is not empty. And that's what you have in the red box. It means that the total intersection of these intervals is not empty. So what is the property for these intervals? So what's interesting is that these intervals do intersect to 2. So here we have a property, the key here in the proof of this Banach theorem. Okay, so here the main ingredient in the proof of the Banach theorem is the interval intersection property of R. So again, what does it say? This intersection property, it says that whenever you have a collection of intervals on the real line, closed intervals on the real line, such that they intersect 2 by 2, their total intersection is not empty. It's a very, very beautiful property, which was used, for example, in cases where we have extensions, but we don't have now any more linear functionals that takes values in R, but takes values in some normed vector spaces, etc., etc. So it's a very, very important property that we even extended to metric spaces, which I may be discussing in some other web notes. Okay? Application of this, let us take the case of normed vector spaces. Okay? So here, let X be a normed vector space. So remember, the proof here of the Banach theorem was done in vector spaces, but now we have a normed vector space, and we can easily take okay, so we have the following. We can take two cases. Either we can take, so if you take f in linear functions on a subspace, okay, So here defined from y into r. Y is a linear subspace of X. So either we take f of y less than the norm of y times norm of f, okay, and to get the following theorem. So this will work. This is your p of y and satisfies all the properties that we want. So we get the following theorem, the one that we will be using a lot in this web notes. Okay, let X be a normed vector space. Okay, let Y be a subspace of X, be a subspace of X. Let F be in Y star equals to B of Y R. So we have a linear continuous functional on Y. Then there exists f hat, which goes from X into R. F hat belongs to X star such that the norm of f hat is less than the norm of f. And this is the amazing part. Okay? And in fact, we don't have the norm of f hat less or equal because it's an extension. So we have, we even have the same norm. And of course, f hat restricted to y gives us f. So it's an extension of the linear function of f defined on the subspace. Okay? So here the amazing part is truly the preservation or the control of the norms. It doesn't, because usually the extension has a bigger norm. The extension has a bigger norm. We have the following corollary. So we have the following corollary. Which is a direct application of this lemma. Let X be a normed vector space. So let's take x0 in X, okay, and norm of x0 equal 1, okay, and alpha 0 positive. Then there exists f in x star such that f of x0 equal alpha 0 and the norm of f equal alpha 0. Okay, so it's enough proof. It's very, very simple proof. Take y equal r times x0, okay, and define set f0 from y into r such that alpha x0 gives you alpha 0. So you can easily show that this is a linear functional and that the norm of f0 is equal to alpha 0, and then you can extend this and you get what you want. So Al-Banach will allow us to prove this. So in particular, what's interesting here is that the shows that in fact x star. So if x star is a normed vector space, I'm sorry, not x star. If x is a normed vector space, then the dual space is not empty. Then it does not have only 0. Then x star has non-zero vectors. So this is due, of course, to Anbanach. One more remark from this corollary. Okay, so here, if another property here, if we choose alpha 0 equal 1 in the corollary, we get what? There exists x star in the dual space such that x star of x0 is equal to 1 and the norm of x star is equal to 1. Okay? We know that for any x star in the dual, okay, we know that the norm of x star is equal to the sup of x star of x when the norm of x is equal to 1, x belongs to x. Okay, so we know that. Okay, but what's happening here is that you can also have now, which is really amazing, we know also that for any x in x, okay, now we can say that norm of x is equal to the sup of x star of x when norm of x star is equal to 1, x star belongs to x. It's really amazing, star. So I mean, not only we have it for the elements in the dual space, we also have it in the elements in the original space. And in fact, one of them is achieved, so it's a max. It's not just the sup, it's a max. This is Anbanach. Okay, Anbanach allows us to say this. Next corollary is useful. Okay, corollary. Let X be a normed vector space. Let X be a normed vector space. Okay. Let x0 be a vector such that for any x star in the dual space, we have x star of x0 equals 0, then x0 is equal to 0. So of course, if you look at here, okay, what we wrote right here, okay, we know that this corollary is obvious because if they are all equal to 0, x star of x are equal to 0, x0, then we get the norm of x0 equal to 0, therefore x0 equal to 0. Okay? Next result is has a kind of geometric meaning. Has a geometric interpretation, theorem. Let X be a normed vector space. Let Y be a subspace of X, be a subspace of X. Let x0 in x such that the distance from x0 to y equal the infimum of the norm of x0 minus y equal delta y in y with delta positive. Okay, then there exists x star in the dual space such that x star of y equals 0 for any y in y, and x star of x0 is equal to delta with norm of x star is equal to 1. So if you don't assume norm of x star equal to 1, then you don't have equal to delta, because we may have different numbers, okay? Prove clearly x0 does not belong to the closure of y. Let y1 to be y plus r of x0, and define f from y1 into r by f of little y plus alpha x0 to be alpha times delta. So we have absolute value of f of y plus alpha x0 equal absolute value of f alpha delta, which is less or equal the norm of x0 plus alpha y over alpha. Oh, let us assume that alpha is not equal to 0. Sorry. Provided alpha not equal to 0. Okay? So f of y plus alpha x0 absolute value is going to be less than alpha. I'm sorry, let's put alpha inside. Okay, let's put alpha inside. So this will give us alpha x0 plus y for any y in y. This is provided that alpha is not equal to 0. Okay? So we assume that, and since f of y is equal to 0 for any y in y, okay, the inequality is still valid. Equality is still valid if alpha is equal to 0. Okay? So this tells us what? That there exists. Now we can use Banach theorem. Okay, implies the existence of f hat from x into r such that f hat of y plus alpha x0 is equal to delta alpha, and f hat of x is less or equal absolute value to the norm of x. In other words, we have the norm of f hat is less or equal than 1. Okay, so but f of x0 minus y is equal to delta, because alpha is equal to 1, which is less than the norm of x0 minus y for any y in y. In particular, if we take the infimum, okay, we get delta less or equal than the infimum y in y, which is exactly delta. Oh, I'm sorry here. I'm sorry. Let's go back here. We need to put norm of f hat. So since delta is positive not equal to 0, the norm of f hat is greater than 1, which implies norm of f hat is equal to 1. So x star equals f hat is the desired element of x star, as thought in the theorem. Another application of these theorems is the following theorem. Let X be a normed vector space. Okay. Let Y be a subspace of X such that for any X star in the dual space, okay, whenever X star reduced to Y is equal to 0, then X star is equal to 0. So, in other words, whenever you have a linear functional equal to 0 on the subspace Y, then it's equal to 0 on the entire space. Then Y, in fact, is dense in X. Okay? Proof. Assume not. So X is different from Y bar. Let X0 belongs to X minus Y bar. Okay? Then we can separate X0 and Y bar. There exists X star in the dual such that X star reduced to Y bar is equal to 0 and X star of X0 equal to 1. And this is of course a contradiction because it's equal to not really. Let me make it be more precise. Okay, so we don't want 1. It doesn't matter. Just any number will do. But let us take it, the one that we just did, x star of x0, to be the distance from x0 to y bar, which is positive. Okay. Then we have a contradiction. Why? Contradiction because x star is equal to 0 on y bar, therefore x star is equal to 0 on y, but it's not equal to 0 on the entire space. Huh? So remark here, if we know that you have a subspace which is dense and x star here is defined from y into r, okay, is a continuous linear functional, then x star has a unique extension to y bar equal x. So in particular, if a linear function is equal to 0 on y, obviously it's going to be 0 on the entire space. It's the other way around. That's amazing. That's really amazing. In other words, we characterizes the dense subspace of x by this property. Okay? Let us look at now at some geometric interpretations of the Anbanach theorem, and specifically on convex sets. So Anbanach and convex sets. Okay, so recall that C subset of X is convex if and only if for any xy in C for any alpha in 0, 1, okay, we have segment basically alpha x plus 1 minus alpha y, which belongs to C. Okay, or the segment xy belongs to C. Let K be a convex subset of be a convex subset of X such that 0 is an interior point of K. One way to do this, take any convex subset of X with a non-empty interior and you can translate it to have a 0 inside. So it's not something like an assumption. This should be looked from a geometric point of view. Okay? So we know that there exists epsilon such that the open ball centered in 0 with radius epsilon is inside K. Okay? Let pk from x into r be the Minkowski function, the Minkowski function of K, so which we studied extensively before. So we have pk of x equal the infimum of alpha positive such that x over alpha belongs to K. Okay? So if x does not belongs to K and 1 over alpha x belongs to K, we must have, by the convexity of K, we must have alpha greater or equal than 1. Okay? That's just the convexity of, because if 1 over alpha x belongs to K and the alpha is less than 1, we can multiply. This will tell us that x belongs to K. Okay? Okay, so pk of x is greater or equal than 1. Okay? Conversely, okay, if pk of x is less than 1, then there exists an alpha between alpha between 1 and pk of x less than alpha less than 1, and pk alpha 1 over alpha x belongs to k. Again, by convexity, because 0 is there, so we have alpha times 1 over alpha x plus 1 minus alpha times 0 belongs to k, or x belongs to k. Okay? So we know that if x does not belong to k, pk of x bigger than 1, and if x is pk of x is less than 1, then x belongs to k. In other words, we have the following x in x such that pk of x less than 1, this is in k. Okay, the Minkowski functional is a continuous function, and therefore this set here, this set is open. Okay, and it's very easy to show. In fact, k interior is x in k in x such that pk of x is less than 1. Okay, and k bar, because of the continuity of k, is exactly the set of x in k in x such that pk of x is greater or equal than 1. So we can safely write that k, in fact, is between these two sets. Set of x in x such that pk of x is less than 1, and x in x such that pk of x is greater or equal to 1. So basically the boundary sits exactly where pk of x is equal to 1 of k. So the first application of the An-Banach, the geometric An-Banach theorem is the following theorem. So we have theorem. Let K be convex, balanced, non-empty subset of X, normed vector space, and let X0, which is not in the closure, okay? Then there exists X star in the dual such that X star of X0 is greater than 1, and absolute value of X star of X is less than 1 for any x in K. This is the first geometric application of the An-Banach theorem. Okay, proof. Since K is balanced, then for any x in K, minus x belongs to K. So x plus minus x over 2 equal to 0 belongs to K. Let x0 not in K bar. Since K bar is closed, the complement is open. There exists R. There exists R positive such that the open ball intersect K bar is empty. Okay? Set K0 is equal to K plus the open ball centered at 0 with radius R over 2, then 0 is an interior point of K0. Okay? Also, K0 is convex and balanced because both K0, B0, the open ball, and this convex set K are both balanced. Okay? Let P0 to be the Minkowski functional of K0, the Minkowski functional of K0. Clearly, P0, okay, is a semi-norm. Okay. Let F be 2R defined by F of alpha x0 equal alpha P0 of x0. Then F of alpha x0 absolute value is equal to absolute value of P0 alpha of x0. Okay, which is P0 of alpha x0. So Banach theorem implies the existence of x star in x star such that x star of x absolute value is less than P0 of x, and x star reduced to the one-dimensional is equal to F. So we must have x star of x0 equal P0 of x0. For any x in K, since K is inside the because the ball centered at x with radius r/2 will be in K0 by definition of K0, so K is inside the interior, so P0 of x will be less than 1, or F of x is less than 1. Okay? Moreover, okay, the triangle inequality, and that's why we divide by r/2. Moreover, we have the distance from x0 to k, okay, k0, this will be greater or equal than r/2. Okay? Indeed, this is just for the sake of being complete to prove this step. Indeed, assume not. Okay, then the distance from x0 to k0 will be less than r/2, and in this case we can find there exists x in k and y in the open ball r/2 such that the distance from x0, which is the norm, the norm of x 0 minus x minus y will be less than r over 2. So the norm of x minus x is less than norm of x0 minus x minus y plus the norm of y, which is less than r over 2 plus r over 2 equals to r. So the distance from x0 to k is going to be less than r, and this is a contradiction. In other words, we're going to find that the ball of x0 to k will intersect k, which we said that it does not intersect k. Okay? So the ball x0r will intersect k, which initially we said that that's not the case. So here, since the distance from x0 to k0 bar is the same as the distance from x0 to k0 greater than 0, so x0 does not belong to k0 bar, which implies that p0 of x0 is greater than 1. In other words, we have x star of x0 is greater than 1. Okay, which completes the proof of our theorem. So we can separate basically a point from a convex set. Huh? Remark: if we take y star to be 1 over p0 x0 x star, then in this case we get a y star of x less than 1 for any x in k, and y star of x0 is equal to 1. Another consequence of the Banach theorem is the following. Result: theorem that X be a normed vector space let A be and B be non-empty convex subsets of X. Assume A is open. I mean, we can, instead of assuming that A open, we can consider the interior of A, and the result will still be valid, okay? Assume that A is open, and A intersect B is empty. So there is no common. But if you go for the interior, you have to assume that B and the interior of A do not have anything in common. Then there exists alpha in R and a functional such that A is included in X in X such that X star of X less than alpha, and B is in X such that x star of x is greater than alpha. Note that by linearity, if we consider instead of x star, we can consider, in other words, the set, if I take minus x star, then I can find another linear function for which the element of A will be bigger than alpha and the element of B will be less or equal than alpha. So it doesn't matter here that one is bigger than alpha, but for sure for the open set, for the interior, in other words, of A, for the open set A, we have strict inequality, and for the B, we have just the large inequality. Okay? Proof. Consider the set C equals A minus B. So this is the union of all A minus B, B belongs to B. Okay, since A is open, A minus B will be open by continuity of the addition and multiplication of scalars, but in this case is the addition. So it's going to be open set, and the union of open set is open. Okay, so C is open. So C is open. Of course, the continuous translation or the addition is an open map. So we're not just using the continuity. Also, C is convex because both A and B are convex. Okay? Since A intersect B is empty, then 0 does not belong to C. Okay? So from the theorem that we just proved, there exists x star not equal to 0 such that x star of x less than 0 for any x in C. So x star of A minus B is less than 0 for any A, B, in A and B in B. So x star of A is going to be less than x star of B for any A in A and B in B. Okay? Since A is open, okay, if we set alpha equals the infimum of x star of B, B in B, then x star of A is less than alpha for any A in A. Indeed, since x star is not equal to 0, there exists x in x such that the norm of x equals to 1 and x star of x is equal to the norm of x star positive. Okay? Let A belongs to A. Since A is open, there exists delta positive such that A plus delta x belongs to A. Okay, so x star of A plus delta x will be less or equal than alpha. Okay, because they are all less than alpha, therefore the supremum is less or equal than alpha, which implies x star of A plus delta norm of x star is less or equal than alpha, or x star of A is less or equal than alpha minus delta norm of x star strictly less than alpha. Next, we discuss some topological properties first one, theorem. Let X be a normed vector space. Assume X star is separable. Then X is separable. Proof. Let xn star in x star such that it's dense. X star is equal to the span of the xn star. There exists xn in x, norm of xn equal 1, and xn star of xn greater than the norm of xn star over 2. For example, let M be the span of the xn's. Okay? Of course, the xn here is for every n. For every n, we use that. So clearly, M is a separable subspace of X. Okay. Let x0 belong to x minus m. Assume that such x0 exists. Then x0 does not belong to m, which is a closed subspace. So the distance from x0 to m is positive. Then by Jan Banach, there exists x star in x star such that x star reduced to m is 0, and x star of x0 is equal to the distance from x0 to m. Okay? Since xn star are dense in x star, so there exists n greater than 1 such that the norm of x star minus xn star less than 1/4. Okay? So f x star xn minus xn star xn is less or equal the norm of x star minus x star n times the norm of xn, but the norm of xn are all equal to 1, which is less than 1/4. Okay? But x star reduced to m is equal to 0, and therefore x star of xn is equal to 0. So absolute value of x star n of xn is less than 1/4. Okay? Which implies, by definition of the xn's, that the norm of xn star over 2 is less than 1/4, or the norm of x star n is less than 1/2. Okay? So the norm of x star less than the norm of x star minus xn plus the norm of x star n, which is less than 1/4 plus 1/2 equals 3/4, contradicting our assumption norm of x star equals to 1. So m is equal to x equals to the span of the xn. Okay, next we introduce what we call the bidual vector space. Okay, which is very natural, the same way we did for x. So x normed vector space. We have x star, which is the continuous linear operators or functionals from x into R. And we introduce the bidual to be the linear or continuous linear operators or functionals from x star into R. Okay? So we know that the bidual is a normed vector space, which is a Banach. Okay? The duals are always Banach spaces because R is complete. And easily we can see that x belongs to capital X. So define f from x star into R by f of x star to be equal to x star of x. Okay. Then f obviously belongs to bidual, and the norm of f is the sup of absolute value of f of x star, where norm of x star less than 1 x star belongs to the dual space, and that is the sup of x star of x, because that's the definition of f, which is equal, from our previous knowledge, to the norm of x. So what happened here is that we have some kind of isometry here between x into the bidual of x. Okay? So the way we just defined it, and therefore we can see, okay, this is here, like it's a natural embedding, which is isometric, okay, and is an isometry. So it preserves the norm, in other words. So from now on, okay, we identify x with I of x, okay, in x star. So we have the element of x will still be called x. We can see them in capital X or in capital on the bidual space. Okay, so the bidual space somehow has this kind of natural embedding. In general, the embedding of x is different from the bidual. Okay? So the case where they are equal gives a new class of Banach spaces, of course, because x double star is a Banach space, so x must be a Banach space. So let x be a Banach space. X is said to be reflexive. If and only if x double star is exactly the natural embedding of x here. Okay? It is very easy to see that if x is reflexive, then x star is also reflexive. In fact, we have more. Theorem. If x is reflexive, then any closed subspace y of x is reflexive. Okay, proof. For any x star in the dual space, x star reduced to y belongs to y star. Okay? Assume that y double star is different from its natural embedding. Let y0 double star belongs to y double star, okay, and y0's double star does not belongs to y. Since Y is a closed subspace, then I of Y, because it's an isometry closed subspace of Y is double star, so the distance from Y0 double star to IY is positive. Okay? What? Go ahead.